Hey, so big shout out to my two co-authors there, the mighty Moss Monaghan and the very complimentary Chris Tanner. Now, why do we mitigate? Well, there's a very simple answer to that, and one is that I need to be able to maintain and improve headroom so that I can produce and produce profitably. I also want to avoid compliance issues. Now, the take-home messages that I want you to have today are very simple, the four of them. One, we must have a very clear objective between impact and the cause, so cause and effect. The second one is that our mitigations need to be chosen on their suitability to an enterprise. They also need to be chosen on their basis of cost effectiveness and not a Ouija board. The third one is that they need to be targeted to the right place and the right time. The fourth one are just some musings and some, I guess, congratulations on the mixed policy approach that's kind of been undertaken in New Zealand. There are 77 different mitigation strategies that we have available to us as of 2012. Subsequent to that, there's probably been about 3 others that have come aboard. They vary in their cost and effectiveness, but there's a general rule in that the more cost effective, the closer they are implemented to the source of that contaminant loss. And as David has already eloquently described, those larger catchment scale mitigations tend to be less cost effective, and there's also the factor that you've not necessarily given up, said that the water quality in between that site of impact and that source, you're not necessarily worrying about that, are you? Now, our current approach to assessing those mitigations are to reduce the complexity, give you some simplicity, and bundle them up into 3 different layers. So the easy, moderate, and the bloody hard. Now, they all have a range of cost. So on the right-hand side, you'll see their cumulative cost for nitrogen mitigations, and you'll see the cumulative reductions that we expect with those. What we've done is we've done this for, in this case, a dairy system. Now, when you compare different enterprises, because there tends to be a little bit more contaminant loss from some than others, then cost effectiveness tends to be inverse in that situation. So there are more options, and it tends to be a little bit more cost effective per kilo of contaminant lost. For example, for deer, easier than for deer, easier than for sheep and beef, perhaps are similar to arable, and horticulture kind of sits in the middle there as well. So our current approach at a coarse, large catchment is to take that very clear objective, codify some farm types, a number of dairy operations, a number of arable operations, vineyards, etc., put them in, and then spit out some numbers. We use a model, could be this one, could be another one. We then say, okay, in that load of N or P or sediment or fecal indicator bacteria, we say, what is the effectiveness and costs of those mitigations here via that bundle? And you've already seen 2 presentations right at the start of the day which translates those loads into concentrations and then also biomass, for example. However, those bar charts that I showed you on the previous slide, those mitigations perform differently depending upon where they are. What you do in Northland does not translate to what you do in Southland. Now, you also, in order to maximise that cost effectiveness of that mitigation, you need to understand the transport pathway. This is quite simple. I'm just going to break it down into those that tend to move over the surface and those that tend to move subsurface. Those that tend to move over the surface, as David mentioned, tend to be rather stickier than those that move and are filtered out through water flowing through the subsurface. So you will have things like your sediment, your phosphorus, your fecal indicator bacteria going overland. Of course, where you can have situations where it is intercepted by, for example, an artificial drainage network. And so then it'll go down macropores and it'll be very quickly transported from that source down through those macropores and out through the tile drain system. Now, there are other things that you need to understand, some caveats around those transport mechanisms. Now, it is true that phosphorus is sticky, and hence you will get delivery of that P in surface waters, and you will get a differentiation between some land use types just simply because they might use more P or there might be more losses associated with that. So this is median concentrations of dissolved reactive P in surface waters. Now, of course, looking at groundwaters, the traditional wisdom was that there wouldn't be any, but there is. There is in some very specific circumstances. And so that's only about 5% of those systems where you have good surface and groundwater interactions that you will see if you were to turn off the tap and mitigate all the P that's being lost in surface waters, you would still see some enrichment via groundwater. Again, only a very small subset of those groundwater sites. Now, we can go along and say, okay, let's implement a practice of restricted grazing. So that's for us folk who live down south where we can't actually grow grass during winter, we grow nasty little Swedes. At least that's what I think of them, having grown up on them. Now, the important point here is that if you're looking at a load basis, implementing a restricted grazing regime of only having 3 or 4 hours instead of 24 hours automatically knocks out 5/6 of the fecal deposits. That means that you can decrease the E. coli load by around 60%. However, if you're looking at the objective, it doesn't matter a hill of beans because who the hell swims during winter, especially in Southland?
Or in summer.
Yeah. That's why I can't swim. No, so let's move on to the use of wetlands. Incredibly efficient and good for many other reasons at removing nitrogen. However, of course, if you don't maintain them well, they can become choked, they can become anaerobic, and what can become a sink for sediment and entrained phosphorus can become a source. Of course, the obvious solution to that is, as David has said there, is to put in sediment traps and to clean them out regularly. Now, let's bring all this together. So we have a hypothesis which is gradually being proven, and this dictates that the majority of our contaminant loads come from the minority of our area, whether that be a catchment, a farm, a paddock, or within a paddock. We call these areas critical source areas, and so we can rank what those sources of contaminants can be from very low to high. We can do the same with those transport pathways, overlay the two, and we can get a reasonable map of to what is happening. Question is, can this aid us in reaching our objective? I'll give you an example. Here are 2 different soil types from a recent sabbatical/sub-holiday I had in the US. One soil which had a fragipan, i.e. that meant there was impeded drainage. Another soil that was free draining. However, if you just looked at the Olsen P concentrations, one was 2.5 times greater than the other. Now, if you just thought about that in terms of sources, I'll just focus on the one that's really high, right? Well, these are the quantities of runoff that were generated in those 2 soil types, nearly 22,000 litres, and NAF all on the other. The load that would be generated, one's 40 times greater than the other. In this case, without taking into consideration those transport mechanisms, you missed the picture. So, in applying that theory around critical source areas, let's just look at some of the numbers. So, is it more cost effective to apply them to critical source areas than to apply them untargeted either across the farm or the catchment? I think you can see where I'm going with this. So, as a very obvious example, this is from a dry stock property. It's a stag there, happily enjoying his afternoon. But of course, he's depositing several nasties in the water as he's doing it. Question around stream fencing. Of course, it is very effective and there's no time lag. Matter of a few days, we've knocked out possibly 95% in this case, sediment, phosphorus, and fecal indicator bacteria, and 70% of ammoniacal N. Let's look at it a little bit more in detail. So, if we applied the mantra of putting those mitigations in on the basis of cost effectiveness, then this is what it would look like. So we had stream fencing all the way down to a constructed wetland at the end there. What we have on the y-axis there is the effectiveness, or the quantity in this case, of P being mitigated. In the yellow, it's the critical source area, and in the blue, it's the farm, so the untargeted loss. What you can see there is that there are similar quantities being mitigated. That's only one half of the equation though. What's the cost? Again, in yellow, that's the cost associated with just targeting critical source areas. In blue, that's the cumulative cost doing it untargeted. Much greater, in fact, 6 to 7 times greater on average. Doing this with real and some modelled data at 14 locations around the country, we can tally it up, and it's quite clear to see that that untargeted approach, yeah, sure, we can knock out about half of the P that's being generated in this case, but it comes at the cost of earnings before interest and tax of 12% on average. And in many of those operations, that was not business as usual, that was no business. Now, in terms of the critical source areas though, similar quantity being mitigated, 40% in this case, but a very small, almost negligible impact on the bottom line. So, how do we do that targeting? Well, it just so happens that one of those advances over the last 3 years since 2012 has actually been some software to take inputs and outputs from models like Overseer, which were, to be honest, spatially very poor, and transform them into tools like this, which tell you where your nitrogen, your phosphorus, your sediment and your E. coli are likely to be coming from on a property basis, then gives you the option of saying, I want to decrease it by 40%, how much is that going to cost me? It'll optimise it and spit out some suggestions. Or someone has come along and said that, your bank manager has said that you've got a certain quantity of money, this is what you can achieve by doing this software, by utilising this software. Now, as I mentioned earlier, I had the opportunity to do a bit of a sabbatical, and so as I was travelling around Europe and the US, I heard many different policy approaches and their opinions of the approach that we've taken. And it boiled down to my interpretation is it was a bloody good job well done thus far. Because prior to that, what we were focusing on are the two ends of the curve here. Focusing on those leaders and impeding or prohibiting those laggards on the basis that the median would shift towards good practice. Now, of course, just doing those two ends meant that an entirely voluntary approach relies on the goodwill of everyone, and it's very hard to discern who's doing what best. And of course, a very intensive regulatory approach tended to stifle innovation, and I had many stories of that coming out of especially Europe. The fix to that was obviously a mixed model, which incorporated components of this, but had that backstop, which was in Europe, that's the Water Framework Directive, it's the Clean Water Act in the Farm Bill in the US, and here we're embarking upon the NOF. Now, one of the councils has gone in and activated rules. Otago has done that fairly quickly. And so what I'm going to show you are a few slides of real data showing you how a farm has actually met that limit that's been put in place. The first thing here was prohibiting bad practice. And so we had our faithful old shittigator here pumping out 130 millimetres an hour. Unfortunately, a little bit of ponding resulted, went down those macropores and straight out into the local stream. Photo there shot by Bob Wilcock. Now, the only thing I want you to notice in this graph are the highlighted bars, which indicate contaminant delivery, but contaminant delivery when it wasn't raining. The only thing that could be contributing those contaminants at that time was that direct influx of effluent. Now, prohibiting that practice automatically knocks out just over 22% of your P, just over 40% of your ammoniacal N, and nearly 60% of your fecal indicator bacteria. That's fairly obvious, but that's only one part of the story. Now, this property also happens to be in an area in the Otago rules which met its nitrogen discharges. That wasn't necessarily a problem for it, but the next problem happened to be DRP, or dissolved reactive phosphorus. Now, this is one of the newer mitigation strategies that we've developed over the last 2 or 3 years, and it utilises the theory that we fertilise on the basis of producing clover. However, we don't need to do that. We can split them out into monocultures. And if you look here, ryegrass performs much better at a lower Olsen-P than does clover. So why not put ryegrass in areas which are likely to produce runoff and clover in other areas? The agronomic advantage of this is that you don't have the shading effect from ryegrass, and hence your clover is able to fully express itself. By decreasing that Olsen-P, you are much likely to have less P loss associated with that red curve there. And indeed, if I was to do that, and so there's the runoff area expanding, as John mentioned earlier, away from the stream. Implementing that split monoculture system decreased our DRP, in this case, by 45%. It increased our profitability, milk solids, by 10%. If you were to do it on a dry stock operation, the modelling thus far would indicate you'd have live weight gains of around 15%. So, tallying all those up, this is what the picture would look like. So, a few years ago, we had concentrations of around 70 parts per billion. The limit was around 26. That was the farm discharge limit. Automatically prohibiting that bad practice had an immediate drop of around 40%. Implementing that monoculture system dropped it even further. And by having better focus on their fertilisation regime, they were able to optimise and decrease their optimum Olsen-P even further decreasing their P losses. The numbers on the top relate to the changes associated with profitability by implementing each of those practices. So you can see that there's some infrastructure costs associated with putting in better effluent systems, but as you go and implement that optimal, or that monocultures in terms of the split pasture system, it very quickly turns into something that's very profitable, and a bit of the saving in terms of superphosphate, you can go in further. So, just to summarise, you need to have very clear objectives so that I can, if I was an operator, I can have the investment signals to be able to make the right and robust decisions. Very clear that we need to avoid obvious bad practice. Mitigations need to be chosen not only on suitability, but not with the heart, on the basis of cost effectiveness. To improve their cost effectiveness even further, we've got some evidence to say that we can do that by focusing on critical source areas. There are some big caveats to that, of course. The very first one is around lags and legacies. In that example that I showed you in Otago, that took 5 years to implement. That may not be quick enough, especially if you don't have the right information or the right quality of data. And having done that, I really do have to ask the question, is it still going to be enough? The comfort I would take that it's not. How robust are those data that I can say I need to invest in different land use practices or even land use change? And I'll leave you with that.